Okay, Camilla, I did get your requests. I now have 6 problems requested. I'm not sure I can do all of them, but I'll do my best. And thank you for the questions. Okay, so we'll get into sharing right away. Mason, welcome. Okay, you should be seeing my screen. I've got a reminder on the bottom there that that was the assignment. And I've got quite a few requests, so I guess we're going to dig into them right away. And I'm going to kind of take them in the order I got them. Somebody asked me about number 19, so I'm going to start with that one. I see we lost Seth. Brandon, welcome aboard. Good to see you. Well, kind of. I can't see you, but good to have you in here. We're going to start with looking. Somebody requested number 19. So number 19 was a limit question. It asked you, find the limit as x approaches 4 from the left. That's what that, remember, that's what that little minus sign there means. Find the limit as x approaches 4 from the left of x squared over x squared minus 16. So approaching 4 from the left means, you know, numbers just slightly less than 4, but approaching it. So for example, like 3.9 and closer. And of course, when you square 3.9, well, you know what happens when you square 4, you get 16. So if you square anything less than that, you're going to get something a little bit less than 16. So when you're doing this subtraction right here, you're going to be getting a tiny negative. That's what I mean. I know this looks like bad math here, but it's a good way to think of limits. It's a real tiny negative number, and on the top, it'll be something really close to 16. And what happens when you divide 16 by a real tiny negative number? Well, a positive by a negative is a negative, and really tiny on the bottom means when you divide by a really small number, you get a really huge number. So this is what I mean by a huge negative number. And of course, the way to write that officially is negative infinity. Now, I'm going to just show you another thing. I mean, that's a pretty good way to analyze it. The other thing you can do is you could look at a graph. And so we just go into our, I'll just come over here into Desmos, and let me put the expression in. X squared divided by x squared minus 16. Whoops. Sorry, x squared minus 16. So here's the graph. Now, as you're if you look at the graph here, and I'll just shove the graph up a little bit. So as you approach 4 from the left, so you're like, I can't draw on here, but if you see my cursor, you're heading to the right. You're approaching 4 from the left, so you're coming in this direction, and you're getting closer to this asymptote over here at 4. Well, as you get really close to 4, how high are we going to be? And you can see we're going to be big time down, and that's why the answer was negative infinity. So as you approach 4 from the left, by the way, if we were approaching 4 from the right, then we'd be coming up here and we'd be way up on the top, and we'd be approaching positive infinity. So be real careful about, you know, the limit as you're approaching. So here we're approaching 4 from the right. Yeah, we're going to be way, way down, and makes sense that it makes sense that our answer should be a negative infinity for that limit. Okay, that's number 19. I don't know. I'm keep my eyes open to see if there's any follow-ups here on number 19. I'm going to go to number 31 next. 31. Another limit problem. Find the limit as x approaches negative infinity of that expression there, 2x over x minus 1 plus 3x over x plus 1. So you can calculate this fairly easily, because as x approaches negative infinity, I mean, on the bottom you're going to have negative infinity and 1. Of course, you know, there is no such thing, but it's just a negative huge number. What happens, you know, on top you're going to have negative 2 times infinity, and you're going to be dividing by a positive 1 times infinity. So you got this negative 2 times this huge number divided by a positive negative 1 times that huge number. Negative 2 divided by a negative 1 is 2. I don't know. Can you tell that? So no, you know, for example, if x was if x was approaching negative 1 million, this would be negative 2 million, and this would be negative 1 million and 1. Well, negative 2 million divided by negative 1 million and 1 is going to be really close to positive 2. That'll give you the idea. And the second fraction, this is going to be what, like negative 3 million on top, and on the bottom it's going to be like negative 999,999, because it's a negative plus a positive. So it's like negative 3 million divided by negative 1. Oh yeah, it's a positive 3, and 2 plus 3 is 5. So again, we could take a look at a graph. Maybe we should. Let's just take a peek at this and see if I can. This is number 31. Okay, so let's go back to Desmos, and let's erase that one. Let's put this 31 in here. So we've got 2x divided by x minus 1. And then to that, we are adding 3x divided by x plus 1. And now you're supposed to take the limit of that as x approaches negative infinity. Okay? So, sorry, what are we supposed to be doing? Am I in the wrong problem? I got to quick go back and take a look. Where were we? Okay. So as x approaches negative infinity, maybe the graph isn't helping us, huh? Let's take a look at that one more time. Okay, let's put the parentheses around the whole thing, not that that'll matter. Yeah, and of course, let's see, do we have to zoom out here? Yeah, here we go. Now I can see what we're doing. Okay, so as x approaches negative infinity, of course we're going to be heading way out to the left here. And I don't know if you can tell, but from the units here, this is at height 5. Do you see that? This is 10, 5. So you can see when we get way out there, yeah, we really are heading for the height of 5. So there's a case where the graph, again, can confirm your suspicions. Okay, so back to our next one I was going to look at is number 55. Number 55. Okay. Let's see, what was 55 doing? It says, sketch the graph of the equation, use the intercepts, extrema, asymptotes, as anything you can to help you sketch this thing. Okay, so the equation is up on the top there. It's 2x squared minus 6 over x minus 1 squared. So do you guys get why I wrote this? Domain issues, right? Because if x was 1, you'd have a 0 in the denominator. So x simply can't be 1. Okay. All right. So what are the zeros of the function? In other words, I'm looking for the intercepts. I'm not doing any derivatives yet, just what are the intercepts? So if you just set the equation equal to 0, which is what I did right here, then you could multiply both sides by x minus 1 squared, and you would have this. And then you could add 6 to both sides. Okay, so there's two places where this thing crosses the x-axis. One is at about 1.73, and the other one's at about negative. So here are the two points that we just found. All right, so we've got intercepts. How about y-intercept? Okay, the y-intercept will happen when x is 0. Well, that's easy to calculate, isn't it? Just plug x equal to 0, and what do you get? On top, you get a negative 6, and on the bottom, you get a 1, and negative 6 over 1 is negative 6. So that's this point. Okay, so we've got one y-intercept and two x-intercepts. Okay, should we now, let's take a look at the derivative. And we also know x can't be equal to 1, so that's why I drew this black asymptote. That's what that dashed line is indicating. So, right, remember we did that way in the beginning. We said x cannot equal negative 1. I'm sorry, cannot equal positive 1. So that's why I have that vertical asymptote drawn on x equals 1. All right, let's take a look at the derivative. So the derivative, unfortunately, you can't see it. It's this quotient up here. So I'm sorry, I can't show you both places at the same time. But you take your number 55. Got to remember where I am. Denominator times derivative of numerator minus numerator times derivative of denominator. Well, the denominator is x minus, hang on a second. The derivative of the denominator is 2 times the quantity x minus 1. So, sorry, this is continued right here. Okay, so this whole first line, I ran out of space. So this is this is times that 2x minus 2 below. Okay, then tried to work this out a little bit. This is that x minus 1 squared right here. And of course I have to take that times 4x, which I did right up here. Minus, and then I had to multiply these two quantities right here. And I came up with that. And then when you combine the numerator, and of course I'm not forgetting, by the way, the denominator over the denominator squared. That comes in right down here. So when I combine these two polynomials here and subtract them, I get this thing divided by the denominator squared. Okay, so when is that equal to 0? First of all, when this is equal to 0, you can multiply both sides by 0 and this denominator will be gone, correct? And then, to make things a little easier, I divided both sides through by negative 4. So 0 equals x squared minus 4x plus 3. So this is just, that polynomial over here divided by negative 4. Well, that's factorable. It's x minus 1 times x minus 3. So I came up with two critical values, two places where the derivative is equal to 0. 1 and 3. Okay. So we have something special going on there. I'm not sure. I can't tell what's. Well, we know at 1 we've got undefined, right? Remember, we have an asymptote, so that makes sense. But at 3 we have something special going on too. And what's the y coordinate for that? Well, if you plug in 3 into the original equation, what do you get? 18 minus 6 is 12 on top, and on the bottom, if you plug in 3, you get 4. And 12 over 4 is 3. So therefore, the point 33 is special. So can I find that? 1, 2, 3, 1, 2, 3. That appears to be that point right there. Okay. Now, what we could do is start filling in more points. But as long as we've done quite a bit here, let's take a look at the electronic graph and see what this looks like. Okay, so this is number 55. Okay. So on here, I guess I don't have, oh yeah, I do up here on the top. So here's number 55 when it's graphed. So first of all, you can see we do have, you can't tell exactly where it is, but you can see there's a vertical asymptote in here. You can't see, you know what, I'm going to zoom in more so we can maybe find coordinate points a little bit better. There. Okay, what did we say? 3, 3. Sure enough, here's where 3, 3 is. Why was that a special point? Because that was the high point, right? And then our y-intercept. So now you're probably wondering, why did we have a point here? That's negative the square root of 3. And then remember we had an intercept right here. Well, you can see that's the second part. I'm going to zoom out a little bit again now. But that was those were parts of that second branch. We know, by the way, this graph will never cross over because we know there's an asymptote. So no matter how far I zoom out, I mean, that's never going to cross over. There's always going to be a separation there. So the calculus, the intercepts, critical points, all of that stuff helped us try to come up with this sketch. Now, the one thing I didn't do is spend more time. We could have, you know, if we were back on our slide here, which I'll go back to now, I mean, we could have picked more points. But you can see we're on a pretty good pattern here. I went up a little too high, obviously, with that black, but you can see we had a good start there. Okay, that was 55. Now, I got 2 more requested. I'm going to pick 49 and go with that, and then I'm going to need to get started on our new lesson, okay? So I'm sorry everybody didn't get their wish, but let's talk about number 49. All right, number 49 on 3-6. What does it say? Again, try to sketch this thing using all those various tools. Okay, here's the function right here. You know, I didn't say it, but what can x not, you know, what's another way to write this? Isn't that y equals 1 minus 1 over x squared? I mean, this is another way of writing what we had right here, correct? Is there anything we have to restrict here, domain-wise? Yeah, x can't be 0 again, so we better say that. X cannot equal 0. That means there should be a vertical asymptote at 0. Let's peek ahead. Sure enough, you can see from our prediction it looks like we have a vertical asymptote. Okay. By the way, do we have any, you know, and I wish I need more space. Do we have any horizontal asymptotes? So what I'm going to do is rewrite this one. I'm going to I need to create a new page. I don't have any space here. Okay, so give me just a second. So what was the function again? 49. We had 3 times the quantity 1 minus x to the negative 2, which is 3 times 1 is 3, and 3 times the other is this. And that is the same as what? 3 minus 3 over x squared. And if we got a common denominator, that is, here, let me change colors so you could think of a 1 being there. We could multiply what? Top and bottom by x squared. So that we'd have a common denominator here. Then it would be what? 3x squared minus 3 all over x squared. So now, do you remember from yesterday, what is our horizontal asymptote rules? Well, when the degree of the numerator is the same as the degree of the denominator, then you look to the what? The ratio of the two coefficients of the of the leading coefficients, 3 over. So we have a horizontal asymptote at 3. Okay. So now we go back to the problem. All right. So now I can sketch in a horizontal asymptote at 3. So you see now I have 2 asymptotes drawn. One at 0, one at 3. Okay, that helps. Unfortunately, yeah. So what about I'm trying to think of it. Yeah, I guess let's look at the function. Here it is. I guess I do have it right. Whoops. I do have it right here. So let's look at that function. What about intercepts? So when will that, let's take the tough one first. When will the y-coordinate be 0? So in other words, x-intercepts. So if you multiply both sides by x squared, you get 3x squared minus 3. And that equals 0. So you add 3 to both sides. And you can see that there would be 2 answers to that, 1 and negative 1. So now, I know it's a little bit hard to see, but this solid horizontal line, that's the x-axis. And sure enough, there they are. 1 and negative 1 are our 2 x-intercepts. Okay. How about y-intercepts? Well, in order to find the y-intercepts, you have to go back to the original function and substitute in a 0. That'll never work because that'll give me 0 on the bottom. So I don't have any y-intercepts. All right, that would make sense because we said the y-axis was an asymptote. Okay, so now it's just a matter of let's start plugging away with some points. So, like what happens when I don't know, you could just pick some points. What did I pick here? 2. If you plug 2 in, what do you get? 12 minus 3 is 9. 9 over 4 is 3. So 2 comma 3. Sure enough, you get that point. Anyway, you just start plugging in points, and then you would get the general shape. And we know that it's not, we'd probably have to pick some points to find out some of these. All right, let's now take a look at the overall graph. What was this? 49. So we'll go back. Let's erase that one. Okay, and what was 49 again? It was 3 times the quantity 1 minus I'm sorry, I'm a little bit slow here today. 1 minus x to the negative 2 power. And you can see our sketch was pretty good, wasn't it? We do have a horizontal asymptote at what? 3, just like we said. See, that's 5. So 3 makes sense. And we do cross at 1 and -1, just like we thought. And if we scoot up, you can, I mean, you're never going to, you can just see that it's approaching the asymptote from both sides, but it'll, of course, never get there because it's an asymptote. So we pretty much have a confirmation. And there is number 49. I'll look at that. All right. Now, let me get back to where we were. Okay, so my apologies. There's a couple more that were requested. I'm running out of, I do need to get going here. So we are now going to take up lesson 3.7. The good news is there really is nothing new here. This is kind of a, like it says, a summary. We're going to bring a whole bunch of tools together. Actually, we were just doing this, so because you guys asked good questions, you already kind of led me into this, and I appreciate that. So what we're going to do is just kind of bring all our tools together and talk about strategies for when you're given a strange-looking thing to graph, you want to pull out these tools and make use of them. The book has a pretty good strategy. I'm going to show you that first. As you, I put the page down so you guys can go look it up later. It's on page 231, right on the first page of the lesson. Guidelines, whenever you're asked to analyze a graph and come up with a graph, here are the three, what? The list of 3 you should always deal with. Number 1, look at the domain and range, which is what we were doing. Remember, is there anything X can't be? Is there anything Y can't be? Now, if it's a word problem, then there is an added complexity, and that is, well, you know, for example, if we were doing a picture frame and trying to find out the equation for the perimeter of it or something like that, you can't have a negative length. Of course, you can. You know, if we're just doing a straight algebra problem, yeah, an answer could be negative. But it's what we mean by a real-life situation. You can't have a negative width or a negative length. So practical considerations might be added to the list. We haven't really done any word problem. Well, not today. We did the other day. Number 2, find the intercepts. And that's what we were just doing. And find the asymptotes. And that's what we were just doing, using some of our new asymptote rules. Remember that little list we came up with? Vertical asymptotes, just the domain, and horizontal asymptotes, we had that little rule. What? If the top had a higher degree than the bottom, then there was no limit. If the top had the same degree as the bottom, then there should be a horizontal asymptote limit at the ratio of the 2 leading coefficients. And if the bottom has a higher power than the top, then there should be a horizontal asymptote of 0. So anyway, we pull those out again. And then number 3 says, hey, you can use your derivatives too to help you out. It says locate the derivatives, locate the values where the first derivative is 0, and that'll tell you if there's a relative high or low. And this is cool. Don't forget to do the second derivative is 0 too. Why? Or undefined. Because when the second derivative is 0, then you've got what? A point of inflection. And that's an important thing to know. That's where the graph kind of turns directions. So this is a good list. I would say keep your eye on this as you work on the next section. So I'm going to we'll start taking a look at an example in the book, and I should have put the page number down. So if you got your books handy, this is just page 232. So on page 232, you'll see this same thing. So in this first example, here's our problem. So let's start applying what we know here. How about domain? Is there anything x can't be in that function? And hopefully you see there's no restriction, right? We don't have any denominators, we don't have any square roots, we don't have any word problem restrictions, so no restriction on the domain. And okay, how about intercepts? And that's what they say. Begin by finding the intercepts. Well, they took the hard one first. Let's do the let's do the x-intercepts. That's when you set the equation equal to 0. And then, of course, factoring is very important. Well, they've already factored it for us. So can you see what are the intercepts? Well, when x is 1 and when x is -5. Okay, so we just gained the point when x is 1. That's this one. See it over there on the graph? And sure enough, that's an x-intercept. And when x is -5. So we've got the two x-intercepts. The y-intercept is easy. I don't know. They didn't spend any time on that. But what's the y-intercept? Just set x equal to 0. Well, this is gone, 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 and all you have left is a 5. So there, now we've got our 3 intercepts. So we already know 3 points. That's cool. All right. Now it's time to look at the derivative. This is an easy derivative. Just use the power rule. 3x squared plus 6x minus 9. When might that be equal to 0, set equal to 0? Well, factor, take a 3 out. I'm not going to spend time on that, but we found out there are 2 critical points, when x is 1 and when x is -3. And by the way, you just go back to the original function and plug in. When x is 1, you get 1 plus 3 is 4. Minus 9 is -5. -5 plus 5 is 0. Oh, yeah. So we're reminded that when x is 1, we're going to be right here. And I drew a wavy line because it's, oh, sure enough, it's got a 0. The tangent line has a 0 slope there. So it's either a min or a max. Well, you can tell from our points it's going to be a min, right? And then, what happens when x is -3? Well, when I'm not going to do it, but you plug in -3, and out comes 32. And again, we have a horizontal asymptote. So what have we just figured out? Oh, that must be the high point. Well, now you pretty much have a picture of the whole thing, don't you? I know it's drawn, but we know it comes up, it hits a max here, it comes down, it crosses the y-axis, it has a min here, and then it had, and you pretty much have what your graph looks like. They have this interesting little analysis. You take the key points, which are what? All the intercepts, and they put them in over here, and they looked at the first and second derivative at each one. So for example, let's look at the point 1, 0. That's this row right here. Just take a look down here. When x is 0, when x is 1, y is 0. What's the first derivative at 0? At 1. You just come up here, what's f prime at 1? Here's the function right here. What happens when you plug in a 1? 1 squared is 1, 1 times 3 is 3. 3 plus 6 is 9, 9 minus 9 is 0. Oh, so we just found, oh yeah, the derivative at that point, it really is 0. So that we should have a horizontal line there. Okay. What's the second derivative at 1? So here's the second derivative. What happens when you plug 1 into that? You get 12, which is a positive. Why is that important? Well, that tells me at this point right here, it's concave up, because it's positive. So now you have no doubts about this curve. You know what I mean? You now have all these cool hints about what the shape looks like. So it's like In effect, what we're doing is we're taking all these tools that we've been working on throughout the entire semester, and we kind of throw them together, and you can pretty easily tell what's going on with this function. Okay, let's take a look at another one here. This is the one we've already done. I'm just adding one feature here. On this, we could have, this is one way we could have factored the thing. Okay, once we knew that one worked, we could have done long division to find the other two factors. I guess that's all. I'm just going to mention that. I don't want to spend too much time on it. All right, we're going to take a look at example 5. This is on a few pages on page 236 in your book. Okay, analyze this. Well, this is a totally different looking graph. We now have something, we have 2x to the 5/3 power minus 5x to the 4/3 power. So a totally different kind of function. Question, is there any restriction on domain? This is a fairly tricky question. I mean, you can take a negative number to any power you want, but what about a root? Remember, when you take something to the 5/3 power, it's like taking it to the 5th power and then taking the cube root, right? Can you take the cube root of negative numbers? You can, because it's an odd root. So what if that was the square root? What if that was a 2 on the bottom? Now we'd be in trouble, because negative numbers, you can't take the square. So do you see how then the domain would have had to been limited to x being positive? So pretty tricky, but because those are odd powers on the in the denominator there, 3 and 3, we don't have negatives and positives are fine, so we don't have a restriction. Okay. Notice what they suggest doing is, let's do some factoring first. So in this line, do you see they've factored out an x to the 4/3? Because 4/3 plus 1/3 is 5/3 for that first number. Why? Because remember, when you multiply two numbers with the same base, you keep the base and you add the exponents. This is all that algebra stuff again. And then, what happens when you take 4/3 and add it to 0? Well, you get 4/3. So that's why that does come out to what it was originally. Okay. So now we're set up nicely. What are the intercepts? You want to find the x-intercepts? Set y equal to 0. So you set each factor equal to 0, x to the 4/3 equals 0, so x equals 0, so there's one of them. And then you've also got this equals 0, which means that if you add 5 to both sides, you've got this. And you can solve that using the algebra they did right here. So basically, we've got two x-intercepts. The first one is right here at 0, 0, and the second one is at 125/8, 0. What is that, by the way? If you divide 125 by 8, it goes in one time, 40, about 16-ish. 15. Okay, so we've got two intercepts. Let's see, do we have any graph down here? Yeah. So here's the 0, 0 intercept, and here's the one that's somewhere in the area of 16-ish. Okay, so we just made use of our little work there. We've got two intercepts. How about a y-intercept? Those are easy. Just plug in 0 for x. Well, 0 to any power is 0. 0 times 2 is 0. This is 0. 0 minus 0, 0. So we didn't really gain anything. We just found out, again, that that point there is both an x-intercept and a y-intercept. Okay, so we've got 2 points. Cool. Let's go to our derivative tool next. Oh, by the way, do we have any asymptotes? Well, remember, we had no restriction on x. And we don't have a fraction, so we don't have any restriction, period, so no asymptotes. Okay, so let's go back to our derivative. I'll leave just enough show here. So as you're doing the derivative, you want to look up here at the original function. And we can use the power rule, can't we? You know what? I'm looking in the wrong spot. Sorry. We want to look up here. Sorry. Let me... This is what you want to be looking at. So as you're doing this derivative, we want to look up here. So we can use the power rule. 5/3 times 2 is 10/3. And then reduce the power by 1. 5/3 minus 3/3 is, you can see why the exponent's now 2/3. And then on the second one, what's 4/3 times -5? -20/3. Reduce power by 1. 4/3 minus 3/3. You're down to 1/3. Okay. So now, set that equal to 0, and then factor. They factored it for us. So this is an easy answer. When is this factor equal to 0? When x is 0. That's that one. And when is this factor equal to 0? Let me do it over here on the side. So that's a what? X to the 1/3? That x to the 1/3 power, that's supposed to be a power, equals 2. So if you cube both sides, it'll be x equals 8. So that's the second one. So okay, so we've got two critical numbers at 0 and 8. Probably looks like a horizontal tangent going on. Okay? They did the second derivative, so you can find out the, here, let me just give an example. We've got these 2 points I circled over here on the left. How do we know if this thing goes up or down? Well, we could look at the second derivative. Take a look at it right here. It's all calculated, but what's the second derivative at 0? Well, what's 0 to the 1/3 power? 0. What's 0 minus 1? -1. And what's -1 times 20? -20. And on the bottom we have an undefined. So undefined. Okay. So that didn't tell us anything. But if we take the other one and plug it in, you're going to see that the second derivative, let's see, where are we? Yeah, so here's where we just found out the second derivative is undefined. When you do it at 16 or, well, they didn't. They just took a point in between at 8. Why? Because that was our critical number. And the second derivative at 8 turned out to be positive, so that told me, oh yeah, this is concave up. And then, wasn't too bad. So you just have to kind of take these little pieces, put them together as best you can, and try to come up with a sketch. And then, of course, when you've done a pretty good amount of work on it, then go ahead and graph it using Desmos or graphing calculator or whatever. So let's just do that real quickly on this one. So I forgot. What number are we on? This is example 5. Oh yeah. Okay, so if we open Desmos, close that off. So we have 2x to the 5/3 power minus 5x to the 4/3 power And you can see pretty much came true just like we said. It has the intercepts at 0 and at 16. Here's that point at 8 where it reached a min. Can you get any idea why this is undefined here? You notice how pointy this is? And any curve that has a derivative is, I mean, why did the second derivative come out to be undefined? Because of this point. As you know, real normal functions don't have a point like that. So anyway, it kind of confirms, if you look back, that's pretty much what we found out using it, doing. So you want to, you know, on a test, yeah, these problems take a while, but you want to be able to pull out your tools. And of course, what I'd be interested in looking at is, did you use your tools? I don't want to see an, I mean, answers are, sure, answers are wonderful, but I want to see that you were able to, you know, do all these things to get there. That's, of course, the whole idea of this chapter and what we're trying to get through. Okay, let's see, do we have time for one more? Let's take one of the problems on the assignment itself. Let's take number 15. Okay, so this is on page 238, number 15. And the directions say sketch this, and it says choose a scale that shows all relative extrema and points of inflection. So in other words, you want to try to show all your key points. So the good news is this one's fairly straightforward in that it's just a straight polynomial. Do we have anything that x can't be here? No. Everything's legal. There is no undefined. So we don't have that to deal with. How about intercepts? Well, it's not quite so easy to see all the intercepts, but we do know that we can find the y-intercept real easily. Just set x equals 0, and you get 0 minus 0 plus 0. So we all know that point's got to be on the graph. Okay, so we at least have one anchor point. So let's get in there and do the derivative and the second derivative. I did them both right away this time. When might the first derivative be equal to 0? Well, I set it equal to 0, and I divided both sides by 4, and then it was not too bad to factor, although it's still tricky. X minus 2 times x minus 2 times x plus 1. So there were two critical points, at 2 and at -1, and here are the coordinates. Okay, so now we have two other points on the graph, and those are probably what? Maxes or mins. All right? So let's take a look at the second derivative, which I have over here on the right. That's supposed to read, let's see, yeah, 12x squared minus 24x. I'm going to rewrite that. That's so pitiful there. So that's 12x squared minus 24x. When is that equal to 0? Well, we can divide everything through by 12. That gives me x squared minus 2x equals 0. And you can see, by the way, that's supposed to be, oh, well, yeah, I didn't, here, again, I didn't show enough. Here, let me, let's do a little better job of showing this. So what you have here is 0 equals x times the quantity x minus 2. And so x equals 0 is one solution, x equals 2. So, and what does that mean when the second derivative is 0? When the second derivative is 0, that means you have a point of inflection. All right, so let's just go over this. We have one intercept at the origin. Here it is. Let me change to red. Here's the origin one, right there. We have critical points at 2 and -1. Here's 2. And -1 is, no, I can't see it real well here. At -11. Okay, it's down here. There we go. All right. And then we found the second derivative. You know, what's the second derivative at 2? That's this point up here. Well, if you calculate it out, what's the second derivative at 2? Here's the second derivative. If you plug in a 2, you get 48 minus 48, which is 0. Aha! So now we know this point right here is an inflection point. So sure enough, do you see how the graph is changing? It's making a turn there. What's the second derivative at -1, which is this one at the bottom down here? Whoops, I just erased. What's the second derivative at, sorry, I'm having a little trouble moving here. At -1, that turns out to be a positive. What does that tell you? It's concave up. Okay, so we're starting to see the whole thing develop. Let's just check that on Desmos. Make a little nicer picture here. Desmos. So x to the 4th minus 4x cubed plus 16x. And then we're going to have to probably do some zooming. Well, you can see all the key points are there. See, we're at the origin is an intercept. Here's that point, -1, -11. And here's that what? That well, I missed it by a little. That inflection point, which is supposed to be right at 2, which I'm not nailing, but you can see it's an inflection point because it's changing from concave down to concave up. Okay, so just get in there. Really nothing new. We're just throwing all these tools together and trying to make us more versatile at graphing. So please don't go to the automation too early, otherwise you're kind of defeating the whole reason we're doing this stuff. And that is to get good at the algebraic viewpoint of it. Now we got to get to an assignment. It's a short one. I've just picked out, I guess, 6. Here they are. 1, 13, 17, 29, 35, and 41. Work on those 6. Okay, questions? Thank you very much for joining me here today. I'll see you tomorrow.